Welcome to Space Dreams Documentary. Tonight we're drifting through the full lifetime of a sun-like star. From steady fusion to a red giant swollen glow, to a planetary nebula's delicate final shell, and into the quiet cooling of a white dwarf. If calm, science-led journeys like this help you relax, please hit like, subscribe, and turn on notifications so the next voyage finds you, and leave a comment with the cosmic story you want next. Now, settle in. The star's long, gentle journey begins. A star begins long before any steady light appears. It begins when a cold cloud stops drifting and starts to fall inward. In a dark lane between bright fields, a molecular cloud spreads like smoke in slow water. Dust threads run through it as narrow bands. Each band absorbs light and leaves a soft-edged shadow. Within one thread, a small bead of gas grows denser. Its outline is not sharp. It is a gradient that thickens toward the center. The first useful fact is simple. Gravity needs only a slight imbalance to start a collapse. The fall is gentle at first. It is more like a slow settling than a plunge. That calm start matters. It allows structure to form instead of a single crash. Across light years, the filament still looks quiet. Inside, the bead motion becomes organized. Gas that once wandered now drifts toward the deepest point. Dust grains drift with it and add opacity. The bead becomes darker against the background. A new scene appears. A flattened veil forms around the center. It is a young disk of material made by tightening spin. Spin cannot simply disappear during collapse. As the radius shrinks, rotation strengthens. Material spreads into a plane and avoids a direct fall. The disk casts a thin shadow line through the surrounding haze. This is the first checkpoint. A forming star is not only a sphere, it is also a plane of orbiting matter. Near the center, the inner rim brightens with heat from infall. Farther out, the disk stays cool and opaque. Its thickness changes with distance and leaves a layered silhouette. At this distance, collapse is visible mostly as shape and shading. Light behaves as a messenger that is easily scattered by dust. Visible colors vanish first. Only deeper warmth can leak through. Even then, the center stays hidden. This is an early limit of observation. Dust blocks direct views of the core. Most knowledge must come from indirect glow and motion. The interior is not resolved in detail, it is inferred from what escapes. While the outside remains cold, the center heats under pressure. Compression turns falling motion into random motion. Temperature rises because particles collide more often. The rise is steady, not explosive. The snowdrift analogy fits. A loose drift compacts into firm ice under its own weight. Air pockets vanish and grains lock together. In the cloud space between particles shrinks in the same quiet way. Another understanding arrives with that image. Heat is not added from outside. It is made by the act of squeezing. The dense center becomes a forming stellar core. It glows faintly, yet the glow is trapped. Photons scatter through layers of gas. They change direction again and again. The path outward becomes a slow, random walk. A second scene appears. Deep inside the cocoon, brightness is softened into a dull amber wash. Outside, the filament remains black and sharply edged. This is another checkpoint. If light cannot leave quickly, the core cannot cool quickly. Trapped energy keeps the collapse from racing ahead. Pressure builds until it pushes back. A balance begins to take shape. Each layer supports the weight above it. This is hydrostatic equilibrium, meaning pressure balances gravity. The definition is short, but the reality has texture. A deeper layer presses outward more strongly. An outer layer presses inward with its weight. When those two meet, the structure holds. That meeting is the second useful fact. A star is a long argument between inward pull and outward push. Some parts of that argument resist intuition. Pressure in the deep core has no simple picture. It can only be compared to a vast weight resting on a tiny patch of matter. No model follows every collision in that region. Instead, only average rates are used to describe the swarm. The forming core continues to warm even as the fall slows. The densest region becomes a hot soup of nuclei and free electrons. Electrons separate from nuclei and move freely. Collisions become more violent. Hydrogen nuclei still repel each other. Most encounters end in a near miss. Yet the hottest core allows rare close approaches. Fusion begins when two nuclei join and a little mass becomes energy. Fusion is the joining of light nuclei that releases energy. Two quick images make it concrete. It resembles two droplets meeting in still mist and becoming one. It also resembles two currents merging into a single deeper flow. Then the reason matters. That released energy replaces what the surface loses as light. A single number anchors the threshold. The core reaches about 10 million degrees before steady hydrogen fusion holds. That is far hotter than a lightning channel in a storm. At that heat matter stays stripped and restless. The core now gains a new kind of stability. If it contracts, it heats, and fusion strengthens. More pressure rises and the contraction slows. If it expands, it cools and fusion weakens. Less pressure follows, and gravity tightens the core again. Another small understanding arrives. Fusion behaves like a self-correcting tendency, not a runaway blast. The star settles into a steady output. The surface marks the last scattering layer for light. Below it, photons still ricochet through dense gas. Above it, they travel outward with little interruption. The boundary is thin, but it has depth. It carries a gradient from hot to cool. Broad overturning flows appear as soft mottling. Warm material rises and spreads. Cooler material sinks and closes the loop. A final scene arrives. The new star's surface shimmers with slow cells and faint dark seams between them. The surrounding cocoon thins and drifts away. The disk remains as a faint flattened ring of leftover matter. In that ring, dust still makes dark lanes and soft shadows. The next stage follows without urgency. The interior must carry energy outward for ages. The rules of that transport shape everything that comes next. A gentle scale shift holds the scene together. A single collision in the core is almost instantaneous. Energy once created can linger inside for a long time before leaving. Across the wider cloud, the change looks small. A dark bead becomes a pale point behind thinning dust. Nothing about the light suggests the crowded interior that supports it. From this steadier glow, the path moves inward again. Rotation and layering now become the quiet framework for the next steps. Steadiness is the quiet signature of a sun-like star. It remains steady because fusion and pressure correct small changes almost immediately. The star hangs in dark space with a clean round limb. Inside, layered gradients replace any simple emptiness. Density is highest at the center and thins outward. Temperature follows the same slope in a softer curve. Energy is born deep within that slope as fresh light and fast particles. That energy does not take a straight road outward. It meets matter that is crowded and charged. Each encounter turns a direct path into a slow wandering. Hydrogen fusion continues at the center, yet only a small inner region produces most power. Outside that region, the star is mostly transport and support. Pressure rises from heat and from the motion of particles. If the core compresses slightly, collisions become more frequent. Temperature climbs and fusion speeds up. More energy appears and pressure increases. Gravity is met by a firmer outward push, and the squeeze eases. If the core expands slightly, the opposite drift follows. Collisions soften and fusion slows. Pressure drops and gravity gathers the core inward again. Stability is not a fixed stillness. It is a continual correction that keeps the star near one balanced state. That correction is gentle. It produces no sharp swings at the surface. A slow visual begins at the center. A bright inner kernel glows behind many layers. A faint halo surrounds it where density begins to fall. Light behaves as a trapped glow in that region. Photons scatter from electrons and ions and change direction. They also lose and regain small amounts of energy in countless exchanges. The result is a diffusing tide of brightness rather than a beam. The process is called opacity. Opacity means how strongly matter blocks light. Fog on a cold morning gives the feeling. Shapes remain present, yet edges blur and distance loses contrast. Opacity matters because it sets the pace of escape. In a sun-like star, a typical photon takes about 100,000 years to reach the surface. That is like a river carving a shallow valley grain by grain. The release at the end is quick. The journey inside is long. This timescale unlocks a useful calm. Surface light is not a direct snapshot of the core. It is delayed and smoothed by the long random walk. Short disruptions in the core fade into the background before the surface responds. Only long trends can imprint themselves on outward brightness. This is also where intuition reaches a limit. Light in open space travels straight and fast. Light inside dense plasma behaves like a restless wandering path. Another limit is observational. The interior cannot be seen in detail. Only surface radiation and the star's overall mass and size constrain models. Opacity itself is not measured directly at every depth. It is calculated from atomic properties and inferred behavior. Small uncertainties in those calculations can shift interior predictions. Energy continues outward through the radiative interior. In that broad region, matter remains stable against large overturning flows. Heat passes mostly by diffusion of photons. The gradient from hot to cool is smooth and persistent. A cutaway view would show concentric shells with no sharp boundary lines. The deepest shells glow more intensely. Outer shells are dimmer and cooler. At some distance from the center, the rules change. Density falls and photons interact less often. Yet the temperature gradient can steepen as the star adjusts. When radiation alone cannot carry heat efficiently, motion begins to help. Convection appears. Convection is heat carried by moving fluid. Warm material rises because it is slightly less dense. It expands as pressure drops. It cools and becomes heavier. Then it sinks and completes the cycle. The everyday analogy is a sea breeze over warm sand. Air rises where the ground is warm. It returns where the ground is cooler. It matters because it carries heat when diffusion becomes too slow. In the star, the pattern is similar. The material is ionized gas. The convective region is not a single churn. It is a hierarchy of cells. Large rolls contain smaller rolls. Edges are soft and shifting. At the base of convection flows turn over and shear. Speed changes with depth in a thin transition layer. That shear is a physical gradient that affects mixing. Turbulence is another place where knowledge becomes indirect. Exact motion cannot be followed for every swirl. Models describe averages and statistical patterns instead. A signal would not trace one clear eddy path through this region. It would be scattered into many possible routes. Even so, the consequences are clear. Convection stirs the outer layers and helps keep composition more uniform near the surface. It also shapes the surface texture itself. Energy that has wandered for ages below now arrives in moving parcels. The surface becomes the visible imprint of those parcels. The main visual anchor settles on the star's visible disk. A pale disk shines with a fine shifting grain, as if covered in slow boiling foam. Bright cells rise and spread. Dark lanes mark sinking flows between them. Each cell has a gentle gradient from center to edge. Near the limb, the edge appears dimmer. Light passes through a longer slant of gas there and loses intensity. The boundary is not a hard line. It is a thinning atmosphere where scattering finally ends. From far away, the whole disk looks calm. Up close, it is always rearranging in quiet cycles. Another small understanding arrives from this surface scene. The color of the light reflects the temperature of the last scattering layer. Warmer surfaces lean toward whiter tones. Cooler surfaces lean toward redder tones. Yet the surface can only report on itself. Deep composition cannot be read directly from the hidden core. Mixing helps bring some material upward. Other elements settle slowly under gravity. Small changes in mixing can alter the surface over a long time. Those changes are slow and subtle. They do not break the star's overall steadiness. The primary analogy of this section rests in geology. The star's power resembles geothermal warmth, rising through thick rock. The source is deep and unseen. The surface shows only the final seep of heat. Channels of transport can shift, yet the outward flow remains steady for ages. The scale shift holds the mind gently. Collisions in the core happen in instants. Radiative diffusion stretches those instants into 100,000 years. Then the final step into space takes only moments. With that steady machine established, the next section moves deeper. The core's chemistry begins to change as helium quietly accumulates. A sun-like star looks unchanging because its changes are hidden in the core. As hydrogen becomes helium at the center, the star slowly shifts even while the surface stays calm. A quiet scene forms in an imagined cutaway. A bright central region is wrapped by softer layers. In the very middle, a paler sphere grows where helium is common. Its edge is a smooth gradient and not a hard wall. Outside that edge, hydrogen remains the main ingredient. Inside, helium collects and does not take part in the same reactions. This is the first checkpoint of aging during the main sequence. Main sequence means stable hydrogen fusion in the core. Stability does not mean stillness. It means the star keeps balance while its fuel slowly changes form. Each fusion event happens quickly. The accumulation of its products happens slowly. The core gains ash in silence. That ash changes the core even before any new fusion begins. A small understanding arrives at once. Helium behaves like a heavier residue that alters pressure for the same heat. The star responds by adjusting its center. Gravity tightens the core a little. Density rises and the central temperature rises with it. Fusion in the remaining hydrogen becomes slightly more efficient. The result is gentle brightening over long time. The brightening is not dramatic. It is a slow drift and not a jump. A second visual anchor appears as a long time lapse. The star's disk remains round and steady. The limb stays softly dim at the edge. Over ages, the overall tone inches toward a whiter light. The change is subtle enough to feel like stillness. Beneath that stillness, the helium region expands. The active fusion zone becomes more concentrated in a smaller volume. The core becomes more peaked in density. The surrounding layers remain layered and smooth. Another understanding follows from this geometry. A narrower active region can produce more power if it is hotter. That hotter core is created by the helium residue. The star is not choosing to brighten. It brightens because gravity and pressure must find a new balance. The process remains gentle because the star self-corrects. If the core contracts too much, fusion rises and adds pressure. The contraction then slows. If the core expands, fusion drops and gravity pulls it back. The star drifts through nearby equilibria rather than leaving equilibrium. The physical boundary inside is important in this drift. The helium-rich center forms a compositional gradient. Material does not mix freely across it. The gradient acts like a calm interface between layers of different density. It limits stirring and keeps the ash near the center. That confinement makes the long trend reliable. Helium continues to collect where it is made. Fresh hydrogen is not easily brought down to replace it. Another quiet payoff follows from that confinement. The future red giant phase begins with the trapped helium center. The star can stay stable for a long time because the outer layers still hold abundant hydrogen. Yet the core is already moving toward a different state. The timescale anchors the whole story. A sun-like star remains on the main sequence for about 10 billion years. That is like many glacier cycles carving and softening valleys on a rocky world. The scale shift is soothing. Reactions in the core occur in instants. The outward glow carries the integrated result of those instants across eons. This long duration is set by fuel and by output. The fuel is the hydrogen available to the core. The output is the luminosity required to balance gravity and transport energy outward. A slightly hotter core uses fuel faster. A slightly cooler one uses it more slowly. The star's mass sets where it falls on that trade. Even within sun-like stars, small differences matter over billions of years. Another visual anchor returns to the imagined cutaway. The pale helium center becomes more distinct. Its radius grows slowly. Around it, a broader region still contains hydrogen. Fusion is strongest near the center of that region. Farther out conditions are cooler, and reactions become weaker. The structure is layered and quiet. The center is dense and bright in the cutaway. The outer layers are lighter and more diffuse. The gradients remain smooth. No sharp boundary appears at the surface. The surface remains calm because transport smooths change. The interior is not sending sudden bursts outward. It is sending a steady flow. The slow drift in brightness is the only outward hint of core evolution. The story reaches a gentle limit here. The deep interior cannot be seen directly through opaque plasma. Only the surface radiation escapes freely. Some information can travel as global oscillations. They are sound-like waves that pass through the interior. The surface can show tiny rhythmic patterns because of them. Yet those patterns do not uniquely reveal every interior detail. Many different internal profiles can match the same surface behavior. Resolution is limited by how waves sample depth. The deeper center is especially hard to isolate. For that reason, the exact size of the helium region is inferred rather than imaged. The inference depends on models of opacity and mixing. Those models carry uncertainties in small details. The broad picture remains steady. Helium accumulates, and luminosity rises slowly. A third visual anchor appears far from the star. The surrounding space stays dark and sparse. The star's light forms a smooth outward field. Dust grains nearby scatter a faint halo. The halo is soft and colour shifts with wavelength. In that region, light behaves as a clean stream after leaving the last scattering layer. It travels straight and without further delay. That clean travel hides the long delay inside the star. The contrast is another small understanding. Escape through space is immediate compared with diffusion through the interior. The star's present light is the end of a long internal journey. Another everyday analogy settles into place. In a quiet cave, a stalactite grows from repeated mineral deposits. Each drop leaves a thin layer. No single drop changes the cave's shape by much. Over long time, the pointed form becomes obvious. The star's helium center grows in the same way. Each reaction deposits a trace of ash. Over eons, the deposit becomes a distinct inner structure. The analogy unlocks a practical point. Growth can be real even when no moment shows a dramatic change. The star's aging works by that kind of accumulation. The final payoff of this section is a calm preview of what comes next. When core hydrogen finally runs low, the core can no longer make energy in the same way. Gravity then tightens the center more strongly. Fusion shifts away from the exact center and begins to favor a surrounding layer. The geometry changes from a central glow toward a ring-like region. The star still looks like a calm main sequence object from afar. Inside, the geometry of energy production is changing from a central glow to a surrounding layer. The next section follows that changing geometry. It tracks how contraction and shell-like burning reshape the star's size and brightness without haste. A star's middle can quiet down while a thin layer around it grows more active. When core hydrogen runs low, fusion shifts into a shell, and the star begins the slow path toward becoming a red giant. The transition starts in an interior geometry that changes almost without surface drama. The helium-rich center is now largely inert for hydrogen fusion. It is dense, and it does not produce much energy by itself. Gravity tightens it and makes it contract. The contraction raises the temperature in a surrounding layer where hydrogen still exists. That layer becomes the new furnace. The new furnace is not a ball, it is a shell, a thin, ring-like zone wrapped around the helium core. Shell burning means fusion occurs in a layer around an inert core. The definition is short and the image is clear. It resembles a glowing band under the skin of an onion. It also resembles a belt of heat around a cooling stone. The reason it matters follows quickly. A shell concentrates energy production into a narrower region. That concentration changes how the rest of the star must respond. The first visual anchor of this section is an imagined cross-section with careful shading. At the centre sits a pale, dense core with a smooth boundary. Around it is a brighter annulus where fusion is strongest. Outside, that annulus brightness fades into broader layers that carry energy outward. The annulus has a gradient from inner edge to outer edge. The inner edge is hotter and more intense. The outer edge blends into cooler gas. The shell is thin compared with the star's radius, yet it dominates the energy budget. This geometry unlocks an immediate understanding. When energy is made in a shell, it pushes on layers above it like a cushion of heat. The outer layers expand because pressure increases in the region supporting them. Expansion cools the outer gas and makes it more opaque. Higher opacity makes it harder for radiation to carry energy. Convection can then deepen and stir larger volumes. The star begins to swell. The surface temperature drifts downward even as total brightness can rise. The star becomes larger and redder, yet it can shine more powerfully overall. The scale shift arrives gently. The shell is a narrow layer that might be pictured as a thin band. Its effects reach outward to an envelope many times larger than before. A small adjustment in a deep layer leads to a large change in the visible radius. That connection is a key part of stellar aging. Another visual anchor settles on the star's surface as it changes. The limb grows softer. The disk appears slightly larger from the same distance. The surface becomes more mottled because convection occupies a thicker region. Darker lanes widen between brighter cells. The edge dimming becomes more pronounced because the atmosphere puffs outward. A thicker atmosphere means light travels through more gas near the limb. Scattering blurs the boundary into a gentle haze. This is another checkpoint. The star's size is not fixed by its outer material alone. It is set by where energy is made and how that energy is transported. Shell burning changes both. The core contraction is also an important hidden part. As the helium core contracts, it becomes denser and more strongly supported by pressure from particles packed close together. The core's response to heat becomes different from the envelope's response. That contrast can confuse intuition. Hotter usually suggests expansion. In the helium core, adding heat does not easily expand the material because density is already extreme. Some of the support comes from electron degeneracy pressure. Electron degeneracy pressure is support from crowded electrons resisting compression. The definition is brief, yet the consequence is large. The core can contract and heat without expanding much. 2 everyday images help. It is like a tightly packed sandbag that warms but keeps its shape. It is also like a jammed pile of smooth stones that cannot rearrange easily. This matters because the core can keep shrinking and heating while the outer star expands. It creates a split personality and structure. One part tightens while another part loosens. A small payoff follows from this split. The expanding envelope cools and becomes more opaque. That traps energy and encourages deeper convection. Deeper convection can dredge up material from below and alter surface composition over long time. The surface becomes a record of mixing rather than a direct record of the core. The star now drifts away from the simple main sequence pattern. Another visual anchor slows down on the boundary between core and shell. The inner edge of the shell is sharply hotter. The pressure gradient there is steep. A thin region marks where helium ends and hydrogen begins. The interface is not perfectly smooth. It can be shaped by gradual diffusion and by limited mixing. The shell itself can be narrow, yet it encircles the core like a glowing collar. In that region, light behaves in a busy way. Photons scatter and the energy flow can be bottlenecked by opacity. Some energy leaves as light. Some energy is carried by moving gas if convection is present above. The journey outward remains slow and smoothing. This is a good place for a limit of observation. The shell cannot be directly imaged. The star's surface hides it completely. Inference relies on models of stellar structure and on subtle patterns in surface brightness and oscillations. Those oscillations sample certain depths better than others. The exact thickness of the shell and the steepness of its gradients remain uncertain in detail. Many different internal profiles can produce similar outward properties. The core's degeneracy state is especially inferred rather than measured. That uncertainty does not erase the broad picture. Core contraction and shell burning are robust results of basic physics. A single number anchors the pace of visible change. The shift from core burning to shell burning and early swelling unfolds over roughly 1 billion years. That is like a slow drift of continents across an ocean basin. The comparison keeps the mind calm. The star changes on timescales that blur any short event. Yet inside reactions and collisions still occur in moments. This contrast is another scale shift. Instant processes in the shell determine trends across eons. Another payoff arrives with a simple cause. The star expands because energy is deposited beneath the envelope. As the envelope expands, it cools. Cooler gas increases opacity. Increased opacity makes energy transport less efficient. That inefficiency forces larger temperature gradients. Larger gradients encourage convection. Convection redistributes heat and changes surface texture. The star becomes redder because its surface is cooler, not because it is weaker. The star can be brighter overall because its surface area is larger. The final visual anchor of the section widens the view. The star's swollen envelope now reaches farther into surrounding space. The atmosphere becomes a layered haze with a gentle density fall-off. The core remains compact and hidden. The shell remains the active ring that drives the swelling. In that region, a signal would not reveal a crisp boundary. It would reveal a smooth transition shaped by scattering and opacity. The story ends this section without suspense. Shell burning continues and the helium core keeps growing. The next section follows the expanding envelope into the red giant phase. It traces how size, temperature and transport settle into a new slow rhythm. A red giant is a quiet reminder that a star can become larger while its core becomes tighter. The swelling begins because a thin shell of fusion heats the layers above it and lets the surface drift outward. At this distance, the star looks like a soft red disk wrapped in a pale, extended haze. The bright limb has no sharp cut. It fades through a thin atmosphere where density drops in a long gradient. Light behaves as scattered glow in that outer veil. Some wavelengths slip through more easily than others. The first checkpoint is simple. Energy is made deeper than before, yet the visible surface moves farther away. The outer gas expands because heat pushes up from below. As it expands, it cools. Cooler gas becomes more opaque and traps radiation more effectively. That trapping steepens the temperature gradient and encourages broad convection. A second checkpoint follows without drama. The star turns redder at the surface even while its total output can rise. The colour shifts because the last glowing layer is cooler. The brightness rises because the surface area grows. The change is a rearrangement of geometry, not a new fuel. The scale of the swelling is large. The radius can reach about 100 times its earlier value, like a sapling widening into a full tree crown. Mass remains close to the centre, yet the atmosphere stretches far outward. The outer layers become so thin that the idea of a single surface begins to blur. In that outer reach, pressure falls so quickly that a small rise in height changes density a great deal. A layer that looks bright at one wavelength can look transparent at another. The photosphere becomes a region with thickness, not a line. In some bands, the star seems to end sooner. In other bands, the halo carries light farther out. A visual anchor settles on the limb. The edge darkens toward a rusty tone and then dissolves into a faint halo. Within that halo, small ripples of brightness drift and soften. The halo is not a shell of light. It is a thickness of gas where photons meet atoms and change direction. Another small understanding arrives. The star looks bigger because the point where light finally escapes has moved outward. Deeper inside, the helium core continues to contract. It becomes denser and more compact than before. That contraction feeds the shell that surrounds it. The shell remains the primary furnace during this phase. Energy created there pushes on a vast envelope above. A second visual anchor forms on the surface texture. Convection cells become broad and slow. Bright patches rise like warm domes. Dark lanes sink between them and form a wandering network. Each patch shows a gentle gradient from center to edge. The pattern evolves, yet it never looks violent. Sometimes the whole envelope swells and settles in slow pulses. Those pulses shift the brightness by small amounts and then let it return. They are driven by changes in opacity in the cool outer layers. Gas alternately traps and releases heat as it compresses and expands. A payoff follows from this breathing. Even mild pulsation can help lift material into the tenuous heights where outflow begins. Convection carries heat in large parcels because radiation alone struggles in the cooler envelope. Transport changes the look of the surface and also the star's response to disturbances. Short changes deep inside are smoothed before reaching the top. Only long trends reshape the visible star. A third visual anchor returns inward as a cutaway. A compact pale core sits at the center. A thin, brighter ring surrounds it where hydrogen fusion is strongest. Outside that ring, the envelope is puffed and layered. The density falls outward in a long taper. The taper is so gentle that many radii can be defined depending on where opacity is sampled. This leads to a limit of observation. The radius of a red giant is not one exact number. It depends on which wavelength is used and on how models translate light into depth. At this distance, a signal would blend light from many layers into one smooth profile. Small clumps in the atmosphere can mimic a larger radius when seen in scattered light. Even the size of convection cells is inferred from subtle surface patterns. Three-dimensional turbulence cannot be fully calculated in detail for every layer. Only averaged prescriptions can be used for the deepest swirls. Despite that limit, one broad result stays firm. The envelope is loosely bound and easy to lift. A fourth visual anchor shows the outer layers beginning to drift away. The atmosphere extends into space as a slow outflow. It is faint and uneven. Denser streams form arcs and partial shells. Between them gaps appear where material is thinner. Farther out the gas cools enough for dust to condense. Dust grains add new scattering and deepen the halo in some directions. Another small understanding arrives. Mass loss begins not with an explosion. It begins as a persistent leak from a vast cool atmosphere. The leak is guided by pulsations and convection near the surface. Those motions can loft gas to heights where gravity is weaker. Radiation pressure on dust can then help the flow continue. The primary analogy of this section stays gentle. The red giant resembles a sea anemone that opens into a wide crown while its base remains tight. The crown is the envelope that spreads and thins. The base is the contracting core that keeps its compact shape. The analogy matters because it captures a split structure. One region loosens and expands. Another region tightens and stores the future. A scale shift deepens the calm. Convection turns over on times far shorter than the age of the phase, yet the red giant state itself lasts long enough for the core to keep growing. Helium continues to accumulate in the center as an inert reservoir. The shell keeps adding to it from above. Pressure rises in the core even as the surface cools. The core approaches a threshold where helium can begin to fuse. That ignition is delayed because the core is supported in an unusual way and does not expand easily. The next section follows that hidden tension. It stays with the compact core as it reaches the moment when helium finally lights and the envelope readjusts. A red giant carries a quiet tension beneath its wide, cool surface. The tension ends when helium begins to fuse in the core and the swollen envelope readjusts. In the center, the helium core is compact in an imagined cutaway. Density rises smoothly toward the middle. The boundary is a gradient rather than a wall. Above it, a thin hydrogen-burning shell glows as a narrow ring. That ring supports an immense envelope that looks soft and inflated. At this distance, the swollen envelope looks almost still. The early answer is simple. The core is held up by a pressure that does not soften when it warms. This support is called electron degeneracy pressure. It is support from crowded electrons resisting compression. It is like grains in a tight sandbank that cannot slip past. It is like a packed swarm that refuses extra squeezing. It matters because the core can heat without swelling much. The tension deepens as the helium core contracts. Contraction raises temperature because collisions become more frequent. The core approaches the threshold where helium nuclei can join. Helium fusion joins helium nuclei into heavier nuclei and releases energy. The picture is difficult to hold in the mind. Helium nuclei repel strongly and must meet at very short range. Only extreme heat makes enough close encounters. The main number is about 100 million degrees. That is far hotter than lightning channels in storm clouds. This ignition can be brief because the core cannot expand easily at first. Degeneracy pressure does not depend strongly on temperature. When helium fusion turns on extra heat, does not immediately cause a large expansion. Energy release rises quickly and the core warms further. Yet the rise does not last. As the core warms, the jammed state loosens. Ordinary thermal pressure begins to matter again. The core expands. Expansion cools it and reduces the fusion rate. The turn is self-limiting and it brings the surge under control. A natural analogy fits this hidden change. It is like an ice dam holding back a river in winter. The ice can thicken and store tension without flowing away. Then a warmer current undermines it, and the barrier relaxes. In the core matter is held in a packed state. Then heating allows a gentler expansion, and the stored tension eases. The main visual anchor is a slow interior bloom. In the cutaway, a bright knot appears inside the helium core. It spreads into a broader glow and then softens. The core's brightness becomes more uniform as expansion cools the center. The hydrogen shell remains a ring, yet its contrast changes. The shell no longer needs to hold up such an extreme envelope alone. A plain consequence follows soon. When the core expands, the envelope above can contract. The envelope is no longer pushed outward as strongly by the earlier shell conditions. The swollen atmosphere begins to settle inward. The radius shrinks somewhat. The surface becomes warmer and less opaque. The limb looks less hazy and the edge becomes more defined. Mottled cells at the surface become smaller and more regular as deep stirring retreats. The star does not return to its earlier main sequence size. It finds a new balance between a compact core and a still extended envelope. Another slow scene forms in the outer layers. The halo around the limb thins. The gradient of brightness at the edge becomes steeper. Scattering still occurs in the upper atmosphere, yet the path out becomes clearer. A second consequence follows soon. Helium burning can now proceed steadily in the core. The energy source shifts from a thin shell to a central region again. The center becomes a calmer furnace rather than a narrow ring. The star's light becomes less dominated by the extreme red giant swelling. It moves to a quieter place in size and color. This phase carries a gentle limit of observation. The ignition occurs deep inside opaque plasma. Direct light from the event never escapes as a clean signal. The surface response is delayed and smoothed by transport through many layers. The event is also brief compared with the star's long life. For these reasons, it is not usually caught as a distinct moment. Knowledge comes from indirect clues. It comes from how many stars are found in each stable stage. It comes from how their sizes and colours cluster over long time. Even subtle, rhythmic surface patterns sample the core indirectly and with limited resolution. Many internal structures can match similar surface patterns. The details of mixing during ignition are also uncertain. The stirring can move material within the core, yet the extent depends on models of turbulence. Those models describe averages and not every eddy. A final visual anchor returns to the interior cutaway, now quieter. The center glows as a smooth sphere rather than a sudden knot. The helium core is larger than before and less extreme in its jammed state. The hydrogen shell forms a dimmer ring around it. Outside, the envelope is still layered and convective. It is less inflated than at the red giant peak. The limb shows a clearer boundary with a thinner halo. Dust and gas still scatter light in the outermost layers. The scattering now traces finer ripples and softer arcs. A calm scale shift closes the section. Helium fusion reactions occur in instants. The readjustment of the whole envelope unfolds over long time. Across long ages, the star spends this chapter steadily converting helium into heavier nuclei, while the surface remains calm. The next section follows this steadier phase. It traces how a stable helium core and a lingering shell share the work until helium runs low again. After the brief interior bloom, the star settles into a quieter shape. Helium fusion in the core becomes steady, and the swollen envelope draws into a calmer size. At this distance, the disk looks less inflated and more defined. The limb still dims gently, and the outer haze thins into a faint veil. Stability returns because the center now makes energy again. The earlier tension of a contracting helium core eases into a new balance. In the deep interior, helium nuclei collide in packed plasma. The triple alpha process is 3 helium nuclei joining into carbon. 3 separate flows become one heavier flow, like small eddies merging into a deeper whirl. The change is rare at first, and then becomes self-sustaining. Energy released in the joining warms the surrounding plasma. That warmth raises pressure and slows further contraction. A quiet payoff follows at once. When the core can support itself with steady fusion, the envelope no longer needs to stay extremely swollen. The star contracts somewhat and the surface warms even while the interior remains layered. A new interior scene appears in an imagined cross-section. A bright central sphere shows a smooth gradient from the very center outward. A surrounding shell of hydrogen burning still forms a thin ring of extra glow. Outside that ring, the envelope is broad and convective but less distended than before. The ring is narrow compared with the star's radius, yet it remains a clear boundary in energy production. This geometry unlocks another understanding. The star can carry 2 furnaces at once, one central and one shell-like. The core furnace sets the overall support while the shell adds a steady supplement. Transport adjusts to this new distribution of heat. Opacity in the envelope drops as the surface warms. Radiation can carry more of the flow again, and convection retreats upward. The surface texture changes with that retreat. Large dark lanes narrow and the bright cells become more regular. The limb boundary sharpens slightly as the atmosphere becomes less puffed. Another slow, visual anchor settles on the disk. It shines in a warm amber tone with fine mottling that drifts slowly. A thin halo surrounds it like pale mist and fades smoothly into darkness. The halo is shaped by scattering in the upper atmosphere. Scattering softens edges and hides where the last glowing layer sits. Even in this quieter state, the envelope keeps moving. Convection continues where radiation still struggles. Warm material rises. It expands and cools near the surface. It sinks again along darker seams and completes slow loops. Those loops do more than carry heat. They mix chemical traces and blur sharp composition boundaries near the top. A second payoff arrives from that mixing. Surface composition can change even when the core remains hidden. Some elements are lifted into view while others sink gradually. The deepest layers do not mix freely, yet the outer region becomes a slow stir. Inside, the core helium burning is also not perfectly quiet. The reaction rate depends strongly on temperature. A slightly hotter pocket burns faster and releases more energy. That extra energy makes the pocket rise and spread. Core convection appears as rolling motion in the bright inner sphere. In a cutaway, the core looks like a glowing fog bank with soft overturning layers. Bright plumes drift upward and blur into their surroundings. Darker patches mark cooler parcels that sink back inward. The boundary between convective core and stable layers is a thin transition zone. It has a steep gradient in temperature and composition. This boundary sets how much fresh helium reaches the burning region. That axis matters because helium is the core's main fuel. A calm scale shift fits here. Individual fusion events occur in tiny instants. The convective turnover takes far longer, yet it is brief compared with the phase as a whole. The stable helium-burning chapter lasts about 100 million years. That's like a great river slowly shifting its channel across a wide plain. During this long chapter, the core gradually fills with carbon and oxygen. Carbon and oxygen are the ash of helium burning. They do not fuse easily at the temperatures reached in a sun-like star, so the ash remains as a growing inner core. The growth is quiet and it reshapes the star's future. Another visual anchor returns to the interior cutaway. A darker central region appears where carbon and oxygen become common. A brighter helium-burning zone surrounds it as thick inner layer. Outside that, the hydrogen-burning ring persists as a thin band. Layering becomes more complex, yet each layer remains smooth in outline. The star is now a set of nested gradients and not sharp walls. This layered picture reaches a limit of intuition. It is tempting to imagine distinct shells like stacked layers of fog. In reality, boundaries are fuzzy and mixing smears them. Some mixing happens through slow diffusion. Some happens through convective overshoot at boundaries. The details are hard to predict. The limit is also observational. The core cannot be seen through the opaque envelope. Only the surface light escapes directly into space. Even global oscillations sample the interior in broad strokes. They do not resolve the exact thickness of each burning layer. Many internal profiles can produce similar surface properties. For that reason, the size of the convective core and the degree of mixing are inferred with uncertainty. Despite that, the main arc remains secure. Helium burning holds the star in a calmer state than the red giant peak. The envelope stays extended but not extreme. The surface stays warm enough to reduce opacity and limit swelling. A final payoff follows from this steadiness. Mass loss continues, but it can be gentler than during the most inflated times. Outflow drifts from the upper atmosphere as a thin stream of gas. It forms faint arcs that expand and fade into the dark. The arcs are not symmetric and their brightness varies with density. At this distance, the star's light illuminates them with a soft glow. Yet the star does not remain in this balanced chapter forever. Helium in the core is gradually consumed, and the ash region grows. When helium becomes scarce at the center, core fusion weakens. Gravity then tightens the inner regions again. Energy production shifts away from the center and returns to shells. The next section follows that return. It traces how two shells begin to operate together and how the envelope expands into a deeper late giant phase. When helium in the core thins, the star becomes layered again in a more complicated way. Two separate burning shells form and the envelope begins a deeper late giant expansion. The star's disk warms and cools in slow drifts as its interior rearranges. The early anchor is simple. Helium burning leaves behind a core that cannot burn further in a sun-like star. That core contracts and a new helium-burning shell appears around it. Above that, the older hydrogen shell persists. The star now carries two active rings instead of one central furnace. The interior looks like nested brightness in an imagined cutaway. At the center sits a darkened core rich in carbon and oxygen. Around it is a helium-burning shell that glows as a thick inner band. Farther out is a thinner hydrogen-burning ring that adds a second layer of power. Outside both rings, the envelope expands and cools. Each ring has a clear physical boundary. Temperature and density change steeply across each band. Between them are quieter layers that mainly carry energy. This geometry unlocks a new understanding. When energy is made in two shells, the envelope responds less smoothly. Small changes in one shell can shift pressure in layers above it. The outer star can swell and settle as the shells compete in their contribution. The star returns toward a red giant-like look, but now it is older and more fragile. Opacity in the cool envelope increases again. Convection deepens again. The surface becomes larger and redder with a thicker halo at the edge. The scale shift remains gentle. The shells are thin compared with the star's enormous radius, yet they decide the visible size and color of the whole object. A main number anchors the timing. This double shell chapter lasts about 10 million years. That is like a long season of tides reshaping a shoreline grain by grain. During that time, the envelope can change noticeably. It can expand to a larger radius than during the earlier red giant stage. The outermost layers become weakly bound. Gravity still holds them, yet only lightly. A visual anchor settles on the surface. The disk appears huge and soft. The limb fades into a broad misty halo. Bright patches on the surface drift slowly and grow larger than before. Dark lanes curve between them and break apart. The pattern resembles slow foam on a calm sea. The halo is not uniform. It shows faint arcs where density is slightly higher. Those arcs are the beginning of detached shells of gas moving outward. Another small payoff follows from this surface scene. The surface is not a solid boundary. It is a region where gas density falls by large factors over short distances. A small change in heating can move the effective surface outward. That makes the star's radius a moving target. It also makes outflow easier. Pulsations become more important now. The envelope can expand and contract in long cycles. Compression raises opacity in cool layers. Heat is trapped for a while. Expansion then releases that heat and the layer cools. The cycle repeats. Each cycle can lift gas to higher altitude. At higher altitude, gravity is weaker, and radiation pressure on dust can push more effectively. Another payoff arrives from that chain. Mass loss becomes efficient because pulsation provides the lift, and dust provides the push. The outflow does not need violence. It needs persistence. A second visual anchor forms far above the limb. A faint shell of gas drifts away, almost spherical but slightly uneven. It carries a gentle density gradient. Clumps appear as brighter knots. Between knots are darker gaps. Farther out, the shell cools and dust grains form. Dust scatters light and makes the shell more visible as a pale ring around the star. The ring expands and fades. New rings can form later. The star begins to surround itself with layered halos like ripples spreading on dark water. The primary analogy of this section rests in music without sound. It is like two slow metronomes ticking at nearby rates. Their combined rhythm alternately aligns and misaligns. In the star, two shells create two separate zones of heat input. Their interaction can modulate the envelope's response. Sometimes the envelope expands more, sometimes it settles. The analogy matters because it captures a beating pattern without implying intent. The physics is still simple. Temperature-sensitive fusion rates can rise with small heating. Rising rates increase pressure. Increased pressure changes density and temperature elsewhere. The system shifts until balance returns. Balance is found repeatedly, yet never at exactly the same place. This leads to a limit of intuition. It is tempting to imagine clear periodicity. In reality, convective turbulence and changing opacity add irregularity. The cycles can vary in amplitude and duration. The interior is also a place of uncertain mixing. Convective boundaries can overshoot. Small instabilities can move material across gradients. Models describe these effects with average parameters. Exact details remain uncertain. The limit is also observational. The two shells cannot be seen directly. The opaque envelope hides them. Surface light and slow variations are the only direct signals. The same surface pattern can be produced by different internal shell strengths. Dust in the outflow can also change apparent brightness by scattering and absorption. That makes it difficult to infer shell activity uniquely from light alone. Even so, the broad structure is robust. A carbon-oxygen core sits at the center. Helium burns in a shell around it. Hydrogen burns in a shell above that. The envelope becomes cool and extended. Mass loss accelerates. Another visual anchor returns to the interior cutaway with a calm emphasis on physical gradients. The helium shell sits close to the core. Its inner edge is steep and hot. Its outer edge blends outward. The hydrogen shell sits farther out with its own steep gradients. Between them is a region where heat must travel through dense gas. Photons scatter there, and convection can carry energy in slow parcels. A signal would not travel cleanly through those gradients. It would be diffused and delayed. This delay smooths the surface response and hides short variations. The story closes with a soft forward step. The star continues to shed its envelope in waves and winds. The core grows more exposed as mass loss removes the outer layers. The next section follows the final deep pulses. It traces how repeated outflows build the material that will later glow as a planetary nebula. The late giant phase ends not with a single burst, but with repeated gentle pulses. These pulses loosen the envelope until the future nebula is already being built in slow layers. The interior has 2 burning shells. Their heat input is not perfectly steady. The helium shell in particular can become unstable, because fusion there is very temperature sensitive. A small rise in temperature raises the fusion rate sharply. That added heat expands the shell and cools it. The fusion rate then falls and the shell contracts again. This cycle creates thermal pulses. Thermal pulses are brief surges in shell burning. The definition is short and the effect is wide. 2 everyday images help. It is like a pot lid that lifts slightly when steam builds and then settles. It is also like a slow bellows that swells and relaxes without noise. It matters because each pulse sends a pressure wave into the envelope. The envelope responds by expanding and then drifting back. During expansion, the surface cools and opacity rises. Radiation becomes less able to carry heat and convection deepens. During contraction, the surface warms slightly and opacity drops. The star becomes a slow breathing object. Each breath is not perfectly the same. The pulses vary because the shells interact and because convection changes the envelope structure. The main number anchors the pace. A strong pulse can recur on a timescale of about 100,000 years. That is like seasons returning in a world where a year lasts longer than recorded history. Between pulses, the star still loses mass steadily. During pulses, the loss can become more pronounced. A visual anchor settles on the star's outermost layers. The disk is huge and red. The limb is wrapped in a thick, hazy halo. The halo shows faint arcs and partial rings. Each arc is a denser sheet of gas moving outward. The arcs are not perfectly round. They are shaped by uneven outflow and by changing opacity. Some regions are brighter where density is higher. Other regions are dim where gas is thinner. A payoff follows from this view. The future nebula is not created in one moment. It is assembled as stacked shells that drift away long before the core is exposed. A second visual anchor moves closer to the surface. Convection cells are broad and slow. Bright domes rise and spread. Dark seams sink between them and form wandering networks. The pattern changes on timescales short compared with pulse recurrence. Yet it changes more slowly than earlier main sequence granulation. The envelope is so extended that a small internal pressure change can lift large volumes. Pulsation adds a global rhythm. Convection adds local texture. Together they loft gas to higher altitudes. At high altitude temperature is low enough for molecules and dust to form. Dust grains add scattering and absorption. Light behaves as a softened glow in dust-rich regions. Some directions look dimmer because dust blocks more light. Other directions show bright rims where dust scatters light forward. Another payoff follows from dust. Dust allows radiation pressure to couple more strongly to the outflow. Photons carry momentum as well as energy. When dust absorbs or scatters, the momentum is transferred to the gas. The result is a steady push that can help gas escape. The envelope becomes a place where gravity is only a weak tether. A third visual anchor widens the view far beyond the star. Several shells are now visible as nested arcs. The inner shell is brighter and denser. Outer shells are fainter and more diffuse. Each shell expands and its density falls. Its edges blur as it mixes with surrounding space. Between shells are gaps of lower density. The whole system resembles the growth rings of a tree, except the rings are moving outward and fading. The analogy is the main one for this section. Growth rings form from repeated seasonal changes. The star's shells form from repeated pulses and winds. The analogy matters because it captures layered history without implying intention. Each ring is a record of a change in outflow strength. Each gap is a record of quieter loss. The interior continues its slow work. The carbon-oxygen core grows but does not ignite further fusion. The helium and hydrogen shells keep operating above it. The helium shell is the main driver of pulses. During a pulse, helium burning surges for a brief time. A convective zone can form between the helium and hydrogen shells. This zone can mix material and change the composition just above the core. Mixing can bring freshly made carbon upward. Later, envelope convection can reach down and dredge some of that material toward the surface. This produces slow changes in surface composition. Another payoff follows from that chain. The outflow carries not only hydrogen and helium, it also carries traces of heavier elements and dust seeds. The departing envelope enriches the surrounding space with new ingredients for future clouds. This part touches a limit of intuition. Mixing in turbulent convection cannot be tracked exactly. The boundary between convective and stable layers is not fixed. It can shift during pulses. Models describe the effect with average parameters and simplified rules. Small differences in those rules can change predicted surface abundances. This is also a limit of observation. The interior shells cannot be seen directly. The presence of pulses is inferred from distributions of stars in different brightness states. It is also inferred from the spacing of shells in surrounding circumstellar material. Yet shell spacing can be distorted by changing outflow speed and by interactions between shells. Dust can hide some shells and brighten others. The true history is reconstructed indirectly. Even the exact timing of pulses can be uncertain for a given star. Despite that, the broad picture holds. Pulses create layered outflow. Mass loss accelerates as the envelope becomes looser. The central core grows more exposed as the envelope thins. Another visual anchor returns inward for a calm cutaway. The carbon-oxygen core sits dark and compact. The helium shell glows as a thick inner band. The hydrogen shell glows as a thinner outer band. Between them a region alternates between calm and convective during pulses. Outside, the envelope is vast and cool. Its density falls outward through a long taper. The taper is so long that the edge feels like a fading mist rather than a boundary. A signal would cross that mist with increasing ease as density falls. Yet near the star, scattering and absorption are strong and the interior remains hidden. A scale shift closes the section. Fusion events occur in instants. A pulse recurrence spans 100,000 years. The layered shells drift outward for far longer than that. The outflow speed is modest, yet time is abundant. Over these long spans, the star loses much of its envelope. The remaining core becomes hotter as it is uncovered. Its radiation grows harder and can ionize surrounding gas once the veil thins. The next section follows the moment when the envelope becomes thin enough to glow. It traces how the layered outflow becomes a planetary nebula and how its shapes are illuminated. A planetary nebula begins as a quiet reveal rather than a sudden creation. It appears when the hot core is uncovered and its radiation makes the departing gas glow. The envelope has already been leaving in shells and streams. Now the light that once struggled to escape can travel outward more directly. The early anchor is clear. The nebula shines because gas becomes ionized and then recombines, releasing light. Ionization is an atom losing an electron. The definition is short and the image can be soft. It is like fog beads briefly holding a charge and then letting it go as a faint glow. It is also like dry grass catching a touch of static and then discharging in tiny sparks that do not burn. It matters because the nebula is not a solid object. It is a thin volume of gas made visible by a changing radiation field. The main visual anchor opens in deep space. A pale ring appears around a dim central point. The ring is not perfectly smooth. It has knots and filaments. Its inner edge is sharper and brighter. Its outer edge fades into darkness through a long density gradient. Some parts look like scalloped arcs. Other parts look like faint sheets. The structure is shaped by the history of mass loss. Earlier shells provide layered density. Later winds can carve cavities and brighten edges. A payoff follows from this first view. The nebula is a map of the graphical past, not a separate life form. Each bright edge marks where a faster flow meets slower material. Each filament marks a density ridge where recombination light is stronger. As the core becomes hotter, ultraviolet photons pour outward. They travel until they meet enough atoms to absorb them. A thin ionization front forms where gas changes from mostly neutral to mostly ionized. The front is not a hard wall. It is a region of steep change. It has a physical boundary in the sense of a gradient. Density drops outward. Ionization fraction drops with it. The front can appear as a bright rim because emission is strongest where ionization and density overlap. Another visual anchor slows down on that rim. The rim looks like a thin glowing lace. Behind it, the interior of the nebula looks fainter and more transparent. In front of it, the outer regions look dark because they remain mostly neutral and do not glow strongly. Light behaves as a sculptor here. It does not push on the gas much compared with its heat. It changes the gas state and thus changes what is visible. The second checkpoint is about time. The gas is moving outward while illumination is changing. A shell that was once invisible becomes luminous when the ionization front reaches it. The nebula can appear to grow quickly, yet that growth is partly a lighting effect. Another payoff follows at once. Apparent size can increase because more distant layers are being lit, not only because gas is moving faster. The main number anchors the outward drift. A typical planetary nebula expands at about 20 kilometers each second. That is like a gentle breeze carrying a drifting curtain across a field. Over 1,000 years, that gentle speed moves gas across a large distance. Over 10,000 years, it builds a structure that is vast compared with the star. The scale shift remains calm. Atomic recombination occurs in moments. The glowing shells persist for thousands of years. During those years, the central core continues to heat as it contracts. It becomes a compact hot remnant. Its radiation hardens and can ionize more deeply. Meanwhile, the nebula thins as it expands. Density drops. Emission becomes weaker. The bright lace fades slowly. Another visual anchor focuses on the filament structure. Filaments are not threads of solid matter. They are regions where density is slightly higher. That higher density yields stronger emission because recombination light depends on how often particles meet. Filaments can form where earlier outflows were clumpy. They can also form where later winds compress the gas. A fast wind from the hot core can run into slower earlier gas and create a shock. The shock heats and compresses material and can create a thin, bright shell. A shock is a sudden compression wave in gas. The definition is brief. Two images make it gentle. It is like a ripple front in shallow water when a wave meets a sandbar. It is also like a soft puff of wind that gathers dust into a thin line. It matters because shocks shape the bright rims and cavities. The nebula often has an inner bubble that looks faint and smooth. It is carved by fast, low-density wind that pushes aside denser gas. The interface between bubble and shell can show a sharp brightness edge. This edge is a physical boundary created by compression and ionization. The next payoff is about color without naming it as a summary. Different elements and different ionization states emit different lines. Yet the eye of an observer is not present here. The physical point is still clear. Emission depends on which ions exist and on the local temperature. Temperature in the nebula is set by a balance between heating from ionizing photons and cooling by radiation. This balance creates gradients. Inner regions can be hotter, outer regions can be cooler. Such gradients change which ions dominate, and thus where emission is strongest. This leads to a limit of observation and interpretation. The nebula's three-dimensional structure is hard to reconstruct from a two-dimensional projection. A ring can be a shell. It can also be a hollow cylinder. Brightness depends on density along the line of sight. A dense clump seen edge-on can mimic a longer filament. Even expansion speed is inferred from spectral line shifts. Those shifts sample only the glowing gas and can miss cooler neutral parts. The central core's true temperature is also inferred rather than directly measured through the surrounding gas. Dust can absorb and scatter, hiding some regions and enhancing others. The reconstruction is indirect and model-dependent. Despite those limits, one arc remains robust. A sun-like star sheds its envelope. The hot remnant illuminates it. The nebula is transient because it expands and thins. The primary analogy of this section is a lantern inside a paper shade. The lantern is the hot core. The paper shade is the layered gas shell. As the lantern brightens and the shade thins, patterns on the shade change. Some regions glow strongly where the paper is thicker. Other regions look dim where holes open. The analogy matters because it captures illumination and projection without implying machinery. A final visual anchor widens outward. Multiple shells are seen as nested arcs. The innermost shell is brightest and most sharply edged. Outer shells are softer and fainter. Between shells, darkness shows where density is low. The nebula expands and the edges slowly blur. Over time, the central remnant will no longer support a bright nebula. The next section stays with that remnant. It follows how the exposed core becomes a white dwarf and how the nebula fades into the background. When the nebula fades, the star's future continues in a smaller and denser form. The exposed core becomes a white dwarf and begins a long, slow cooling. The envelope is now far away and thinning into darkness. The central remnant is compact and hot at first. It has no fusion left to power it. Its light comes from stored heat and from slow contraction that is nearing its end. The early anchor is plain. A white dwarf is supported mainly by electron degeneracy pressure. Electron degeneracy pressure is support from crowded electrons resisting compression. It is like a library shelf filled so tightly that no book can slide inward. It is also like a packed crowd that cannot make room without someone leaving. It matters because the remnant can remain stable without fusion. Gravity presses inward. Degeneracy pressure pushes outward. The balance holds the object at a small size. A visual anchor settles on a stark scene. A tiny bright point sits at the center of a faint expanding shell. The shell is the old nebula. It is now a thin lace and it spreads outward. Its edges blur as density drops. The central point is the white dwarf. It is much smaller than the earlier star. Its light is intense per unit area, yet its total output is modest compared with the red giant phase. The remnant has a layered structure. A carbon-oxygen interior holds most of the mass. Above it lies a thin layer of helium. Above that lies an even thinner skin of hydrogen. The boundaries are gradients. Diffusion slowly sorts elements by weight. Heavier ions sink, lighter ones rise. The surface can become very pure in one element because of this sorting. Another payoff follows from this quiet layering. The surface composition can become simpler over time even as the interior stays mixed from earlier burning. The white dwarf also has a new way of losing energy. Photons leave from the surface. Neutrinos can also carry energy from the interior in early cooling. Neutrino emission is energy carried away by weakly interacting particles. The definition is brief. It resembles heat disappearing through a wall that ordinary light cannot cross. It also resembles a scent leaking through a sealed box while air stays inside. It matters because early cooling can be faster than surface light alone would suggest. The white dwarf begins very hot. The surface glows with harsh ultraviolet and then with bluer light. As it cools, it becomes fainter and redder. There is no new fuel to reverse the trend. Cooling is the new life. The main number anchors the size in a gentle way. The radius is about the size of Earth, like a marble compared with the earlier swollen star. The mass is still comparable to much of the original star's mass. Density is therefore extreme. The idea of density becomes hard to hold. A small spoonful of white dwarf matter would outweigh mountains. That image reaches beyond intuition, and it needs care. The better calm understanding is structural. The same mass is now held in a much smaller volume. Degeneracy pressure makes that possible. The scale shift is soothing. Earlier fusion in a core sustained brightness for billions of years. Now stored heat leaks away over billions of years. The process is slow and quiet. A visual anchor moves closer to the limb of the white dwarf. The edge is sharply defined because the atmosphere is thin. Limb darkening exists, but over a smaller scale. The atmosphere is a shallow layer where pressure drops quickly. The surface can show subtle gradients if magnetic fields are present, yet those are not required here. The key physical detail is the steep pressure gradient. A small change in depth corresponds to a large change in density. Light behaves in a simpler way than in a giant envelope. Photons travel through a thin atmosphere and escape quickly. The surface light is more directly linked to surface temperature. The interior is still hidden, yet the link between surface and interior is closer than in a main sequence star because the object is compact and transport distances are short. Another payoff follows from that compactness. Cooling is more uniform and less affected by large convective envelopes. The white dwarf has no vast atmosphere to buffer changes, yet a new complexity appears as it cools further. The interior can crystallize. Crystallization is ions forming an ordered lattice as they cool. The definition is short. It resembles molten glass slowly becoming rigid. It also resembles a quiet pond freezing from within. It matters because crystallization releases latent heat and can slow cooling for a time. In the interior, carbon and oxygen ions can arrange into a solid lattice while electrons remain free and provide pressure. The crystallization front moves outward as the object cools. It creates another layered boundary. This boundary is not a shell of burning. It is a phase change boundary between liquid and solid. A visual anchor holds this interior scene. A solid core forms as a darker region within the cutaway. Around it remains a liquid mantle of ions. The boundary is a smooth front. It moves outward slowly. Heat flows through it and escapes at the surface. Another payoff follows. Even in a dead star, internal rearrangement continues. Structure can evolve without fusion. This leads to a limit of observation. The interior crystallization cannot be seen directly. The white dwarf is too small for direct imaging of its disk in most contexts. Information about cooling and crystallization is inferred from populations and from subtle oscillations in some objects. Those oscillations probe internal structure indirectly and with limited resolution. Many interior profiles can fit similar observed patterns. Cooling ages depend on models of atmosphere opacity and on assumptions about composition. Small changes in those assumptions shift the inferred age. Dust and faint gas around the remnant can also alter apparent brightness in some directions. Thus, the cooling history is reconstructed, not directly watched. Even so, the broad arc holds. The white dwarf is a stable remnant supported by degeneracy pressure. It cools by radiating heat and by neutrino losses early on. It can crystallize as it cools. Meanwhile, the Planetary Nebula continues to expand and fade. Another visual anchor returns to the nebula at large distance. Its filaments are now faint. The ring edges are diffuse. Density is lower, and recombination light weakens. The shell mixes with surrounding space and becomes hard to separate from the background. The central white dwarf remains as a small, steady point. The primary analogy of this section rests in a coal ember after a fire. The ember holds heat for a long time. It glows at first and then dims. No new flame appears, yet the ember persists. The analogy matters because it captures long cooling without drama. The next section follows the fading nebula as a physical object. It traces how the expanding gas loses its glow and merges into the wider medium, leaving the white dwarf alone in darkness. The nebula does not vanish so much as it becomes ordinary. Its glow weakens as the shell expands and the central remnant cools. The reason is simple. When gas thins, atoms collide less often, and fewer photons are released. At this distance, the nebula appears as a broken crescent of light. The curve is thin and uneven, as if the shell is torn open. The rim is brighter than the interior because the line of sight is longer. One side holds a sharper inner edge. The other side dissolves through a wide gradient into darkness. Filaments cling to the curve like quiet threads of frost. Knots hang along the arc, and each knot carries a soft halo. A curved arc can remain visible after most of the shell has faded. Brightness comes from a layered depth, and not from thickness alone. Inside the shell, the glow is gentler and more even. The cavity seems clear because density is lower and emission is weaker. A closer view settles on one filament near the rim. It is a narrow ridge with a darker lane beside it. The ridge has a crisp crest and a blurred skirt. That crest marks a place where gas is slightly compressed. Compression raises density and increases how often particles meet. Recombination explains why meeting matters. Recombination is an electron returning to an ion. It is like dew forming as the surface cools and moisture gathers. It is like a faint shimmer appearing when scattered droplets settle together. It matters because recombination produces much of the visible glow. As the shell expands, recombination slows. Fewer ions and electrons meet each second. The same gas then shines less, even while it keeps drifting outward. Recombination happens in brief instants. The fading of the nebula unfolds across many thousands of years. The main number is about 25,000 years. That is like the time a glacier needs to soften sharp ridges in a valley. During that span, the shell becomes larger and thinner. Density drops and the brightest rims lose contrast. The nebula fades mainly because of dilution rather than disappearance. Some of the gas also becomes neutral again. The central remnant cools and its ionizing radiation weakens. An ionization front begins to retreat through the shell. An ionization front is the boundary between ionized and neutral gas. It resembles a thin frost line that shifts as conditions change. It resembles a moving shadow edge cast across a dusty haze. It matters because the glowing region can shrink while the shell expands. A layered rim becomes visible in the dim light. A bright arc sits inside a darker outer layer. Beyond the arc gas is present but mostly unlit. Inside, the arc gas remains ionized and ready to recombine. At this distance, light behaves as a marker of state and not of mass. Two regions can hold similar amounts of gas and look very different. Darkness in the shell does not mean emptiness. It often means the gas is too cool or too neutral to radiate strongly. Within the densest knots, recombination continues a little longer. A knot dims from its outer halo toward its denser center. The rim becomes a chain of small islands of glow. Between islands, the shell turns almost transparent. Background starlight passes through with little scattering in the thinnest regions. Where dust remains, the starlight softens into a faint milky wash. The ionization front can leave behind a cooler neutral wake. In that wake, atoms hold electrons more often than they lose them. Momentum carries the gas onward even after the glow declines. The shell keeps expanding even when it no longer announces itself with light. The shell also begins to mix with its surroundings. The interstellar medium is the thin gas and dust between stars. It is like still water receiving a spreading stain of silt. It is like quiet air taking in a drifting cloud of pollen. It matters because mixing erases sharp boundaries and smooths contrasts. At the contact surface, shear can wrinkle the edge into curls. Those curls stretch into wisps and then break into smaller patches. Each patch fades as density falls and as ionization weakens. Scattering by dust can soften the rim and widen the halo. Absorption by dust can hide parts of the shell and deepen nearby shadows. These effects change the apparent shape without changing the overall drift. A wide view holds the nebula again as it grows fainter. The rim is now uneven and scalloped. Small protrusions reach outward like soft fingers of haze. Behind them, the shell looks patchy and porous. Detached arcs from earlier pulses can still be traced far out. Each arc is a thin sheet with a brighter inner face. Each arc has a fading outer skirt that blends into the background. Over time, arcs overlap and their edges lose identity. The primary analogy of this section is a ripple pattern in wet sand. A passing wave leaves ridges that look sharp for a moment. Then gentle wash levels them, and the pattern becomes smooth again. The analogy matters because it captures a temporary imprint on a larger field. This stage also reaches a limit of observation. The faintest gas is hard to measure because emission depends strongly on density. Neutral material can be nearly invisible without strong excitation. Projection adds ambiguity because three-dimensional shells overlap along the sightline. One bright arc can be a true rim or a long filament seen edge on. Dust can absorb and scatter, changing which regions appear bright. For these reasons, the remaining mass is inferred with uncertainty. Even the edge of the nebula is a definition and not a wall. It is placed where brightness falls below the background and the shell disappears. A final visual anchor holds the last stage. The shell is now only a faint arc with no sharp edge. It is a barely visible gradient that stretches into darkness. At the center, the white dwarf is a small, steady point of light. The surrounding space looks calm again as the shell blends away. The next section stays close to that point. It follows the long cooling of the white dwarf as it releases its remaining heat. A white dwarf begins as a bright ember of compressed matter and then turns into a quiet archive of fading heat. Cooling is the only long story left because fusion has ended and the remnant is stable. At this distance, the object is small and sharp-edged. Its light is clean compared with the old giant envelope. The surface radiates energy away, and the interior slowly follows. The early anchor is simple. The white dwarf cools because stored thermal energy leaks out through a thin atmosphere. Heat flow inside is dominated by conduction rather than broad convection. Conduction is heat carried by direct particle motion in dense matter. It is like warmth spreading through a solid rock by touch alone. It matters because the interior can share its heat efficiently. The cooling therefore depends on the total heat content and on how easily the surface releases it. A visual anchor settles on a stark scene. The white dwarf is a tiny hard point in a wide darkness. The last filaments of nebular gas are so faint that they no longer glow. Only a slight uneven haze remains at great distance. It drifts outward and thins into the background medium. The central point holds a steady brightness at first. Its limb is crisp because the atmosphere is shallow. A small payoff follows. When the atmosphere is thin, surface temperature tracks the interior more directly. The remnant does not hide behind a swollen envelope any longer. The skin of the object is a steep gradient. Pressure and density rise rapidly below the surface. Light escapes from a narrow layer where the gas becomes transparent. Above that layer, the density drops quickly and scattering becomes weak. This physical edge makes the object seem more like a bead than a cloud. Another visual anchor moves closer to that limb. The rim shows gentle darkening toward the edge as the path through the atmosphere lengthens. The atmosphere is so shallow that small changes in composition matter. A surface made mostly of hydrogen can have different opacity than one made mostly of helium. That difference changes how quickly heat can radiate away. Another payoff follows. The same interior can appear brighter or dimmer depending on the outermost skin. Cooling is therefore not only about the core, it is also about the thin blanket at the surface. This blanket is not thick in size, but it sets the rate of loss. Inside the dominant support is still electron degeneracy pressure. That support does not need heat. As the white dwarf cools, pressure support remains. The remnant shrinks only slightly because degeneracy does not behave like ordinary gas pressure. The energy loss mostly lowers temperature and luminosity. The scale shift remains gentle. Individual photons leave in moments. The overall dimming unfolds across immense time. A main number anchors that time. The white dwarf can take about 1 billion years to cool from very hot to far less luminous. That is like the time needed for mountain ranges to rise and wear down. During this span, the surface color shifts from harsh blue-white toward a duller tone. The total brightness drops by large factors. Yet the object remains present and stable. Another visual anchor opens in an imagined interior cutaway. The center is dense and mostly carbon and oxygen. The outer layers are thin shells of lighter elements. Within the deep interior, ions begin to arrange into a lattice as temperature falls. Crystallization forms a solid core surrounded by a liquid mantle. The boundary is a smooth front with a steep change in state. It moves outwards slowly as cooling continues. A small payoff follows. Crystallization releases latent heat and slows the decline for a while. The remnant does not cool at a constant pace, it cools in chapters. In one chapter, neutrino losses can dominate when the interior is hottest. In another chapter, latent heat from crystallization becomes important. In later chapters, the remaining heat is low and the decline slows again. The pacing is not dramatic. It is simply shaped by which energy channel is most efficient at a given temperature. A primary analogy can hold this without human objects. It is like a warm basalt boulder after sunset. The surface cools first and becomes rigid. The interior stays warm and feeds heat outward through the solid. At first, warmth streams away quickly. Later, the boulder feels almost cold even while it still releases heat. The analogy matters because it captures conduction and a changing cooling rate. Another visual anchor widens to the surrounding space. The white dwarf sits inside a region that looks empty, yet a thin medium is always present. The remnant moves through it and the medium drifts past. The density is so low that it barely affects cooling. It does, however, become the eventual home of the atoms once shed by the star. The old shell has expanded so much that its boundary is no longer a rim. It is a long gradient in density. A signal would cross that gradient without noticing a sharp edge. Only in denser knots would scattering still be noticeable. Another payoff follows. The star's earlier mass loss becomes part of the general medium long before the white dwarf has cooled much. The visible nebula is a short episode compared with the cooling era. The nebula may glow for tens of thousands of years. The remnant cools for billions. This contrast is a quiet kind of closure. A short, bright flourish becomes a long, dim persistence. This chapter reaches a limit of observation and inference. The white dwarf is small and can be faint. Distance estimates and atmosphere models strongly affect the inferred luminosity. The cooling age depends on the assumed composition of the surface layer. It also depends on the internal mixture of carbon and oxygen, and on how crystallization proceeds. These details cannot be observed directly. They are reconstructed from light curve spectra and population statistics. Those reconstructions have limited resolution. Different interior profiles can produce similar surface temperatures. Dust or faint gas along the line of sight can also alter apparent brightness. For these reasons, the cooling history is a model guided by light, and not a direct measurement of the interior. Even so, the broad behavior remains robust. The remnant cools, it dims, it changes state inside. It remains stable because degeneracy pressure does not fade with temperature. Another visual anchor returns to the crystallization front inside the cutaway. The solid region expands. Its lattice is not visible as a pattern. It is only implied by the phase change boundary. The boundary is smooth and slow. Heat flows through it and out. The outer layers remain fluid longer because they are less dense and they cool differently. Over time, more of the interior becomes solid. The surface continues to radiate. The rate of radiation falls as temperature falls. Each drop makes the next drop slower because the surface emits less energy per unit time. A final payoff arrives. Cooling is self-slowing. The remnant becomes a long-lived faint object rather than a brief flare. The next section moves even farther in scale. It follows how the white dwarf continues toward extreme dimness, and how the star's full life reads as a single arc from fusion to quiet heat. The last light of a white dwarf is not a dramatic ending. It is a gradual settling toward darkness as heat becomes harder to notice. The early anchor is simple. The remnant cools until it nearly matches its surroundings in temperature. Thermal equilibrium means matching temperature with the surroundings. It resembles a warm spring pool mixing into a broad cold river. It also resembles a small pocket of warmth in a deep cave wall. It matters because cooling eventually slows when contrasts fade. A visual anchor forms in a quiet cutaway. The interior is now mostly solid. The crystallized region fills almost all the volume. Only a thin liquid layer remains near the outer depths. The boundary between solid and liquid is smooth and rounded. It moves outward and then nearly stops as temperatures drop. The surface sits above this interior like a thin skin. The skin is an atmosphere only a shallow distance thick. It has a steep density gradient. A narrow layer does most of the radiating. The limb looks crisp because the emitting layer is thin. A small payoff follows. The remnant remains stable even when its heat is low. Degeneracy pressure still supports it and does not depend on temperature. Gravity still presses inward with the same pull. The balance remains, only the glow changes. Light behaves as a slow report of heat loss, and not as a sign of internal burning. A second visual anchor widens outward from the cutaway. The nebula has long since blended into the surrounding medium. No rim remains and no filaments glow. Space looks uniform and quiet. The white dwarf appears as a dim point. Its colour shifts slowly toward deeper red as the surface cools. Its brightness falls, and then falls more slowly. Another payoff arrives. Cooling is self-limiting because radiation weakens as temperature drops. Each new step takes longer than the last. Energy leaves in tiny packets as photons. The total number of photons per second declines. The remnant becomes harder to distinguish from faint background light. Yet the object is still there. Its small size remains. Its sharp edge remains. The difference is only contrast. A third visual anchor returns to the surface layer. The atmosphere is stratified. Lighter elements float above heavier ones. The surface can become dominated by hydrogen or helium. That surface choice changes opacity and changes cooling speed. Opacity is resistance to light passing through material. It is like fog that blocks a lantern without touching the lantern. It is also like a veil of dust that softens a sharp beam. It matters because the thinnest skin controls how fast heat escapes. Another payoff follows. Two remnants with similar interiors can dim at different rates because of their surface layers. This makes the cooling story depend on details that are hard to see. Cooling also interacts with the solidifying interior. As more of the interior becomes crystalline, latent heat is released and delays further cooling. That delay is gentle but real. It spreads the dimming over longer spans. The scale shift remains calm. In the lattice, ions settle into ordered positions separated by tiny distances. In the surrounding medium, atoms drift across immense gaps. Between these scales, the white dwarf holds a steady compact form. Another visual anchor shows the crystallized interior as a faintly textured sphere. The texture is not literal lines. It is the idea of a lattice filling the volume. Near the boundary, the solid and liquid meet in a thin transition region. Heat flows through this region by conduction. It moves from the deep interior toward the surface. The surface radiates it away. Another payoff follows. The white dwarf behaves more like a cooling rock than like a star. It has no internal engine. It has a stored reserve. It releases that reserve slowly through a small surface area. The cooling pace is long compared with the earlier luminous phases. The main number anchors the far horizon. Reaching near invisibility can take about 1 trillion years, like a shoreline being smoothed by wave after wave until sharp edges become dust. This number is not a promise of an observed future. It is a projection from physical models. The time is far longer than the visible nebula era. It is far longer than the main sequence era. That contrast carries another payoff. Most of a sun-like star's life is spent in steady fusion, yet most of its future is spent cooling quietly. This is the longest tale of the story. Here a new term appears with care. A black dwarf is a white dwarf cooled to near invisibility. It resembles a stone that has finally reached the same temperature as its cave. It also resembles a dark seed resting in cold soil with no warmth left to give. It matters because it names the theoretical endpoint of stellar cooling. The idea of a black dwarf also brings a limit of observation. The cosmos is not yet old enough to contain true black dwarfs in the strict sense. Even very cool white dwarfs remain warmer than the deepest background. Their faint light can still be detected in principle. In practice, detection is limited by confusion. and by background glow. A faint remnant can be lost among countless dim sources. Its distance can be uncertain. Dust along the line of sight can absorb and redden its light. A small change in assumed atmosphere composition can shift the inferred temperature and age. Interior composition also matters. Carbon and oxygen ratios change heat capacity and crystallization behavior. Those ratios are inferred indirectly. They are not measured directly in the core. For these reasons, the late cooling curve has model uncertainty. It is guided by physics and by population patterns, not by direct interior images. Another visual anchor returns to the remnant in the wider field. The point of light is now extremely faint. It sits in a region where the surrounding medium is nearly featureless. A slight gradient in background brightness crosses the field, from distant starlight scattered by sparse dust. Against that gradient, the remnant can disappear at some wavelengths. It can reappear at others. The object does not change quickly. The sense of vanishing comes from contrast and from the limitations of inference. Another payoff follows. Darkness in astronomy often means a lack of contrast rather than an absence of matter. The remnant remains a compact mass. It continues to shape nearby trajectories through gravity, yet it offers little light. The story of the star is now mostly written in what it has already released. The gas and dust it shed have mixed into the surrounding medium. The heavier elements it made remain in that medium as well. The white dwarf keeps only a fraction of the original heat. It releases that fraction slowly. The section closes by widening the timescale once more. Billions of years pass like a slow dimming. Trillions of years stretch beyond easy intuition. The next section gathers the whole arc. It returns to the calm sequence from fusion to quiet remnant and lets the narrative settle into rest. A star like the Sun ends as a small, dense remnant not because it collapses violently, but because it runs out of fusion pathways. The whole arc is a sequence of pressure balances changing step by step. The early anchor is simple. Fusion provides outward pressure for most of the life, then electron degeneracy pressure takes over at the end. A visual anchor opens in a wide, silent field. A faint point of light sits alone. The surrounding space is almost uniform. The last traces of the nebula are gone into a smooth background. The point has a crisp edge and no visible halo. It is a white dwarf, compact and steady. Around it, a thin interstellar medium drifts in slow gradients. Dust is sparse. The background glow is gentle and uneven. A small payoff follows. The final state looks simple because the complex stages have already been spent into the environment. The remnant keeps mass and gravity. It loses most other drama. The story can now be traced backward from this quiet point. The path begins with a core where fusion turns hydrogen into helium. That early phase lasts the longest. It is a steady engine that keeps the star in balance. Heat pressure in the core pushes outward. Gravity pushes inward. The surface remains stable in size and brightness for a long span. The scale shift is calm. Nuclear reactions happen in tiny volumes and in tiny moments. The visible star shines steadily across billions of years. A second visual anchor forms as an internal cross-section. Layers appear. A bright central region produces energy. Above it sits a radiative zone where photons diffuse outward slowly. Farther out sits a convective region where hot gas rises and cooler gas sinks. The boundary between these zones is not a wall. It is a gradient in opacity and temperature. The surface is a thin shell where light escapes. Limb darkening shows that the atmosphere has depth. Light comes from slightly different heights at different angles. A payoff follows. The visible disk is a measurement of transport and not of core size. The core is small compared with the whole star. The surface is where energy finally becomes light. When hydrogen in the core becomes scarce, the balance shifts. The core contracts and heats. The outer layers respond by expanding. The star becomes a red giant. A third visual anchor appears in that phase. The star's surface swells. The photosphere cools and reddens. The edge looks less sharp. A diffuse atmosphere extends outward with a soft gradient. Convection creates mottled patterns. Large cells rise and fall. The star's luminosity increases while surface temperature falls. The payoff follows. Brightness and temperature can move in opposite directions because size changes. The red giant phase introduces a new core process. Helium begins to fuse into carbon and oxygen. In a sun-like star, the core is dense enough that electron degeneracy affects the onset. The ignition can be rapid compared with the slow earlier pace, yet the surface does not explode. The energy goes into reorganizing the core and lifting degeneracy. The outer layers remain bound. The star continues. Another visual anchor shows the star later on the giant branch. The envelope becomes unstable. Pulsations expand and contract the outer layers. Each pulse moves the photosphere outward, then inward. The atmosphere forms thick shells of gas and dust. Those shells drift outward. Their edges are marked by density contrasts. The rim of each shell can scatter light and appear as a faint ring. The payoff follows. The star loses mass through repeated gentle shedding rather than a single event. Over time, the envelope becomes thin. The core becomes exposed as a hot compact object. Ultraviolet radiation from the core ionizes the earlier ejected gas. A planetary nebula forms. The word planetary is historical and does not describe planets. It is an ionized shell of gas around a hot remnant. The nebula's bright rim comes from geometry and density. The line of sight passes through more material near the edge. The interior looks dimmer because it is thinner. Filaments and knots form where density is uneven. These structures create sharp boundaries and shadowed lanes. Light behaves as a tracer of ionization and recombination. Recombination is an electron returning to an ion. It resembles frost forming along a cold edge as vapor settles. It resembles a thin sheen appearing on a surface as droplets gather. It matters because recombination produces much of the nebula's glow. A payoff follows. The nebula shines because energy from the hot remnant is absorbed and re-emitted. It is not a fire, it is a conversion of radiation into visible light. The nebula is short-lived compared with the star's earlier stability. It expands and thins. The glow fades as density drops. The shell blends into the interstellar medium. The remnant remains. It becomes a white dwarf. A visual anchor returns to the compact point. The atmosphere is shallow. The limb is crisp. Beneath the atmosphere, density rises steeply. The core is supported by electron degeneracy pressure. This support does not require heat. The white dwarf cools by radiating stored thermal energy. Conduction carries heat outward through the dense interior. Crystallization begins as the interior cools. A solid lattice grows outward from the center. Latent heat slows cooling for a time. Cooling continues for immense spans. A main number anchors the contrast. The glowing nebula can fade in about 25,000 years like a ripple on wet sand smoothing away. The white dwarf can cool for about 1 billion years before becoming far dimmer, like a slow evening that never quite ends. These numbers are rounded anchors. They guide scale more than detail. A limit of intuition and observation sits softly in the center of this arc. The deep interior of a star is never seen directly. Core composition and temperature profiles are inferred from models. For white dwarfs, atmosphere composition affects inferred ages. For nebulae, faint neutral gas can be invisible. Projection makes shells appear as rings. Dust can absorb and scatter. Many different internal arrangements can produce similar surface light. The story is assembled from indirect signals and from populations. Its broad steps are strong. Its fine timing has uncertainty. A payoff follows. Even with these limits, the arc holds because it is built from balances and energy flow. Gravity compresses. Fusion releases energy. Transport moves that energy outward. Mass loss reshapes the outer layers. Degeneracy pressure supports the final core. Cooling releases the last stored warmth. The final visual anchor is a slow, wide shot. The compact point remains. No ring surrounds it. No shell glows. A faint gradient of background light crosses the field. In that region, the interstellar medium carries atoms once forged in earlier stages. Carbon and oxygen drift as part of the larger cycle. The white dwarf stays quiet and small. Its heat leaks away slowly. The scene contains no urgency. It is steady and calm. The narrative settles into the sense of a completed journey. The first fusion flames have long passed. The final remnant remains as a cool, compact record of that history. The darkness around it is not empty. It is a wide reservoir of thin matter and long time. The arc closes without a cliff edge. It rests on equilibrium and gentle fading into a larger quiet field.